Okay, let's get started. So today we'll talk about enzyme kinetics, and we'll study how fast an enzyme can catalyze a reaction. And so in the last lecture, I talked about how enzyme catalyze reactions, and I show you that reaction coordinate, and you see enzymes catalyze reactions by lowering the energy of activation of the reaction. But enzymes cannot change the equilibrium, the KEQ of the reaction, because it cannot change the delta G of the reaction. So here I show you this is you see this is a plot of the velocity of an enzyme catalytic reaction as a function of the substrate concentration. And again, you see this hyperbolic curve, just a similar curve as we saw for the oxygen binding by myoglobin we derived previously. And today I will show you how we describe the velocity of an enzyme catalytic reaction as a function of the substrate concentration. So one very important concept about the enzyme catalytic reaction is every enzyme have a catalytic active site. And the substrate have to bind there, and then the reaction will occur, and then the product will be released. So before I start to talk about enzymes, I'll give you a brief overview of the basics of chemical kinetics of chemical reactions. And so we start with very simple first order reaction, the transformation of this reactant A to the product B for this reaction. And so the velocity of the rate of the reaction can be defined as the rate, how fast this product accumulate. You see, this is the velocity equals the derivative of concentration of B as a function of time. So that is the rate of how fast this product accumulate. For example, in the unit of mole per second. And so because this is a very simple first order reaction, for every A transformed, you get one B. So in a similar fashion, you can also describe the rate of the reaction as a function of concentration of A. So that is how fast A disappears equals how fast B accumulate for this simple first order reaction. You see, this is the negative concentration over time. That is, this describes how fast A disappears, and that describes how fast B accumulate. So we can actually, we talk about this in the previous lecture. For the velocity of reaction, it can be described as a function, as a product of the rate constant multiplied by the concentration of the substrate. So for this first order reaction, the unit of K is in the inverse of time, as I show here. And so for this equation, we can do an integration, and then we can then describe how fast A disappears or how fast B accumulate. And so we can integrate this equation, both sides of this equation, over a certain time period of time from 0 to T. And then we have, what we have is, you see, this is log A over A naught. A naught is the starting concentration of A. And this A is concentration of A at any time we are studying. And this log A over A naught equals negative K1 times T. T is the concentration. And so this is the one form of the equation. You can also describe the equation in another form, which is the concentration of any time of concentration of A at any time equals A naught multiplied by e to the power of negative K1 times T. T is the time. So if you know the A naught, if you know K1, you know T, the time you are looking at the concentration, and then you can calculate A at any time of this for this reaction. So these are two different ways we describe the rate of the first order reaction. And so now let's look at graphically. And for this first order enzyme other reaction, this is not enzyme catalyzed reaction. It's simple first order reaction. The concentration A as a function of time equals A naught times e to the power of K1 times T. So this is the plot. You see that's the concentration of A, and that is the time in seconds. And if you do this plot, it is like this. And you see the concentration of A gradually decrease as a function as the reaction proceeds. And so with this equation, actually you can calculate how much time is needed for half of the A to be transformed into a product. So the half-life of A equals 0.693 divided by the rate constant K1. So for this simple first order reaction, the half-time of the reactant is a constant. It is only related to the rate constant, and it's not related to the concentration, how much you start with. So this is the half-time of this first order reaction. And so if you do this, do a plot of log A as a function of time, and then you have this linear curve. And you see the slope of this curve actually equals negative K1, of the rate constant. So if you have a lot of experimental data, you can do this kind of plot, and then you can actually measure the rate constant of a certain reaction. So this is you see the x-axis, the y-axis is log A, it's the concentration. A equals, it means the concentration of the reactant at a certain time. And you see as the reaction proceeds, you get the concentration of log A becomes smaller and smaller. So this too, it's the same equation, you just have same equation, you show it in different ways. So that is first order chemical reaction. Is there any questions before I move on? So I want to refresh your memories. How do we deal with the rate of chemical reaction? With this we use this first order reaction as an example. Any questions before I move on? Okay, if there's no question, we'll move on. So now let's look at the initial velocity of enzyme of a reaction without enzyme. So this is uncatalyzed first order reaction of transforming A to the product. And so we know the velocity of the reaction equals K times the starting concentration of the reactant. So for the velocity of reaction, initial velocity, and then you can, at any point at certain concentration, you can calculate velocity by multiplying the concentration of A by the rate constant of the reaction. So this is for uncatalyzed reaction. But if you have enzyme catalyzed reaction, and you see a very different curve for the simple first order reaction, which is catalyzed by enzyme. And again, you see this y-axis is the initial velocity of the reaction, and the x-axis is the concentration of the substrate of the reactant. And here you see for the enzyme catalyzed reaction, we see this hyperbolic curve. And we see this, like you see in the very beginning, as you increase the concentration of the substrate, and then the rate of the reaction increased very quickly, and gradually it plateaus out. And at a very high concentration of the substrate, and you see, even if you increase, you do not see an obvious increase of the velocity. So these two kinetics is very different. And you see with some enzyme around, and then you have this hyperbolic curve. So the job today, what we'll work is, we will figure out how to describe this kinetics property of the enzyme catalyzed reaction. So No, let's look at the enzyme catalytic reaction. And you see we have, for this reaction, you add some enzyme with the substrate. And then the enzyme will associate at the active site of the accept pocket with the substrate. And so this ES complex can either dissociate to form to the starting point to form enzyme and substrate, or it can react with the active site of the enzyme to form this product. So generally, this binding process is a faster process. It's pretty fast, and but the formation of the product is a slower step of the reaction. And so, because we're only looking at this V0 is like when you mix the reactant and the enzyme, and then immediately you look at how fast the reaction goes. So we want to look at the initial velocity, not the velocity when the reaction reaches after a certain time. And so in the very early stage of the reaction, because the product concentration is very, very low, so we have very little bit of the product. And then the concentration of this product is negligible. So the enzyme catalytic reaction can be simplified. And so we just assume this process is very, very slow because there's very few product formed at this stage. And then we can simplify this equation. You see, now for the enzyme catalytic reaction, this is simplified mechanism. And enzyme bind to the substrate to form this ES complex. And this ES complex can either react, the enzyme can catalyze the formation of the product and then release the product. Or it's also possible for the ES to decompose into the enzyme and the substrate. So we want to simplify this equation because it will be easier for us to describe this enzyme catalytic reaction mathematically. And also we have some very important assumptions when we describe the enzyme catalytic reaction mathematically. And so here I show you this is the graph showing the concentration of, for example, of a substrate as a function of time. And so you see in the very, very beginning, you have very little bit product, and then gradually the product accumulate. And eventually it just, reaction do not complete, and then you do not have any product formula. And then you see, this is magenta color, that is the concentration of substrate. And you see the substrate concentrations drops gradually until it's completely consumed. And so if we look at the very early stage of the reaction, let's focus on this part of the reaction. And this is the zoom in view about how fast the product forms. And you see this blue curve, that's how fast the product curves. And this is purplish color, that's the concentration of free enzyme. And this green colored curve, which is the concentration of the ES complex. Both of these are difficult to measure quantities. But if we do the experiment, we know how much enzyme we add. So the total amount of enzyme can be easily derived based on how much we added. And you see in the very beginning, the enzyme bind to the substrate very quickly. And then the enzyme catalytic reaction reach a steady state. You see this ES complex, it remains almost, do not change at a certain level. And so in this kind of stage, so the product is constantly consumed and the substrate is consumed at constant rate, and product is formed at constant rate. So this is a steady state assumption. We assume the concentration of ES complex does not change as a function of time. So this is the rate of ES concentration as a function, change as a function of time. So, but like if we assume this steady state, and then now we can derive the velocity of the reaction, which equals K2 times ES. Because the second stage of the reaction is a slow process. This is a slow process. So the rate of the formation of product is dependent on the rate limiting step of the reaction. So now we have this description of what's the velocity of the reaction. This initial velocity of enzyme catalytic reaction equals K2 times the concentration, ES. And so now look, you see, this is this unsteady state, the ES concentration is almost constant. And then if we want to figure out the velocity, we just need to figure out what's the concentration during a steady state of the reaction for the ES concentration. And then we can calculate the rate of the reaction. Any questions about steady state assumption? So we have two assumptions now. The one assumption is that we assume the reaction between product and the enzyme to form ES complex is very, very slow in the beginning of the reaction. So we can ignore this step of the reaction. The inverse of this second step. And then that is a simplified form of the enzyme catalytic reaction. And now, based on our observation about how fast ES forms, and then we have a steady state consumption. We assume at the time period we study this problem, the concentration of ES does not change. So that is a steady state assumption. And then we have the equation. Now V naught equals K2 times ES. So we can describe the rate of the product formation by multiplying the ES concentration by the rate constant K2. So now let's see how we derive the equation to describe the velocity of this enzyme catalytic reaction. So this is a simplified form. We ignore the reaction between product enzyme to form ES. And so each of this step of the reaction, we can describe it as we describe for the simple first order reaction. So for the formation of ES, it equals K1 times the free enzyme concentration multiplied by the substrate concentration. So that corresponds to this step of the reaction. So that is one process which results in the formation of ES. And you see it equals K1 times ET. ET is a total concentration of enzyme when you start the experiment. And so the free enzyme, of course, equals ET subtract by the fraction of enzyme already associated with the substrate. And this is a substrate concentration. And so this is the formation. This is like for this complicated process, this is the only one step which results in the formation of ES. And there are two steps which consume ES. So you see the ES can react can dissociate to form E and S. And the rate constant for this reaction is K minus 1. And of course, ES can also react at the enzyme active site to form a product. And so the rate for this process is determined by the K2, rate constant K2. So now let's look at the rate of ES breakdown. And it equals K minus 1 multiplied by the ES plus K2 multiplied by ES, because we have two steps which consume ES. And this is the reaction which results in the formation of ES. Because based on the steady state assumption, and we know the rate for the formation of ES and the rate for ES breaking down is the same, because the ES concentration does not change by time. And that means the formation rate and the breaking down rate is the same. So now we have this equation. It's pretty complicated, but it is one side is how fast ES forms, and then the other side is how fast ES get consumed. So now with this equation, we can actually figure out what is ES. So we can work on that equation by rearranging the equations containing the terms containing ES, and then we have K1 times substrate concentration plus K minus 1 plus K2 multiplied by ES concentration equals K1 multiplied by ET, which is the total enzyme concentration, multiplied by the substrate concentration. So now we can solve this equation for ES because we, as I said in the steady state assumption, it is very important. If we want to figure out velocity, we have to figure out what's the concentration of ES. And then we multiply ES by the rate constant, and then we have the velocity. That's why we are working on these equations to derive ES. So you see this is the ES, and we can divide this part by this, divide this by this part, and then we have the ES concentration. And so, of course, you can further simplify this equation by arranging, by dividing each of these by K1. And then we end up with ES concentration equals ET, total enzyme concentration, multiplied by the substrate concentration over substrate plus this constant, K minus 1 plus K2 over K1. So this is the constant. All is for a certain time, at certain temperature, these are constant, all constant, because you see this, like K1 plus K2 over K1, these are all rigid constant. If you divide this, add this together, they are still a constant. So we introduce another constant, and we can replace this K minus 1 plus K2 over K1 by this constant called Km, and it's called the Michaelis-Menten constant. And then we have this much simplified version of the reaction of the equation, which is ES equals ET multiplied by substrate concentration over substrate concentration plus Km. So now we put this ES into the equation. V naught equals K2 times ES, and then we have a description of the velocity of the enzyme catalyzed reaction as a function of substrate concentration. And you see, this is the rate constant of the second step of the reaction, and that is the Michaelis-Menten constant. It equals K minus 1 plus K2 over K1, and that S is the substrate concentration. And this ET is the total enzyme concentration used for this experiment. So now we have a pretty simplified version of the equation to describe the velocity of the reaction as a function of substrate concentration. And so for this equation, we can simplify it further by defining Vmax. Vmax is the maximum velocity of the enzyme catalyzed reaction, and it equals K2 times ET. So that is the highest possible rate of the reaction, which can be achieved if you do the experiment. And so if we replace K2 times ET by Vmax, and now we have very nice and simplified equation, which is V naught equals Vmax times substrate over Km plus substrate concentration. So this is what we call Michaelis-Menten equation. That is the equation we describe the velocity of enzyme catalyzed reaction. So I want to slow down here a little bit. If you have any questions about any step of how we derive the Michaelis equation, and you can ask a question. Any questions? I hope to slow down a little so that you can digest what we did, how we derived this equation.
Which equation do we have to per se know? Because I know most of them are just deriving them to get to this final equation. So which one will we have to, I guess, understand or know them?
So you have to understand, eventually, you have to be able to understand and you apply this equation for various kind of problems. Yeah, you don't need to know derive precisely how it works, but you have to know the steady state assumption. What is steady state assumption? And
right.
Yeah, what we how we simplify the equation is the problem, so that we can simplify the. So because we ignore that step for the between the reaction between the product, and then this equation can be handled. This process can be handled a lot easier than if we include that step.
Exactly. So just knowing where each, I guess, component comes from to make
for example,
this
you
equation.
need to know what is Vmax. That is very important. So that is the maximum velocity which can be achieved by this reaction. It equals K2 times ET. So that's one thing you need to know. And the other thing, very important thing, you need to know what is the Michaelis constant. So we put together all those constant part as one. We combine them, and we use the Km to describe K minus 1 plus K2 over K1. That is the Michaelis constant. Of course, it have its experimental meanings, and I'll show you that in a moment. So first we need to know what's the steady state assumption, and then then you will know how we derive the equations. And you need to know what's the definition of the Km, and then you need to know what's the meaning of Vmax, and then of course you need to remember this equation, the Michaelis equation, and apply it to solve problems. Any more questions before I move on? Is there any other questions? So now you see we have very nice, clean, simplified version of the equation, which can be used to describe the velocity of the reaction as a function of substrate concentration. And so if you do a set of experiment and you measure the velocity of reaction as a function of substrate concentration, and then you'll end up with this hyperbolic curve, which can be described by this Michaelis-Menten equation. So here this V naught, which is the initial velocity of the reaction at substrate concentration S. Vmax is maximal velocity of the reaction when ES equals ET. So that is every single enzyme bound to a substrate. And then you see when the substrate concentration is very high, and then the rate of the reaction is pretty close to Vmax. And so the definition of Km equals K minus 1 plus K2 over K1. So this is actually means the rate for the formation, for the ES formation over ES just like decomposition over the rate for ES formation. And so there's a very interesting point to note is that if you look at the substrate concentration at half Vmax. So if you look at the rate of the substrate concentration of the reaction at half Vmax, so you just replace this V naught by half Vmax, and then you immediately derive Km equals Ki equals substrate concentration. So I'll show you in a moment. So if you have you measure the substrate concentration of half Vmax, and then you see the Michaelis constant equals the substrate concentration. So this is actually the experimental meaning of Km. Km equals the substrate concentration at half Vmax. And also, if you do the experiment at very high concentration, which is way larger than Km, and then you see the velocity of the reaction equals Vmax. So it's predicted from that curve we already showed you. If you have a lot of substrate around, and then the velocity of the reaction is very close to Vmax. And also, if you do the experiment at very low concentration of substrate, which is way lower, smaller than Km, and then the reaction can be reduced to a simple first order reaction. You see the velocity equals Vmax divided by Km multiplied by the substrate concentration. This only, like, it's only only when the concentration of the substrate is very low, way lower than Km, and then you see there's a linear relationship between velocity and the substrate concentration. So these are three of the scenarios, and we can derive about the velocity as a function of substrate concentration. And so when substrate concentration equals Km, the velocity is half Vmax. When substrate concentration is way larger than Km, and the velocity is approaching Vmax. And when the substrate concentration is way smaller than Km, and then there's a linear relationship between velocity and the substrate concentration. So there are three conclusions we can derive based on the mechanics-mental equation. Is there any questions about this? I'll slow down to allow a few questions. Is there any questions? Okay, so if there's no question, this is, if you apply the mechanics-mental equation, this can be easily derived. And so
what does double greater than or double less than sign mean?
What's your question?
What does the double greater than or the double less than sign mean?
Oh, this is way smaller. For example, you have Km equals 1 millimolar, and then you have substrate which is like a 0.01 molar. So it's way smaller.
Oh, okay, thank you.
For example, under this condition, you have a substrate concentration which is 5,000 times Km. So if substrate is 5,000 Km, then Km plus S is only 5,001. And you can easily assume that it equals 5,000. So that's how it works. And then the substrate concentration cancels out, and then you have a velocity almost equals Vmax. Okay. So we know this velocity as a function of substrate can be described as by the mechanics equation, mental equation, and which is that hyperbolic curve. If you do a set of experiment, and then you can, with that curve, you can actually estimate Vmax. So with this curve, you can actually estimate Vmax, because this is approaching plateau, and that is pretty close to Vmax if you like extrapolate this. And you can also, based on this curve, you can also estimate what is Km by looking at the substrate concentration and half Vmax. So, but we want to do a better job to determine the exact number of Vmax and Km. And then there's a very nice way you can do that, is that you can do a double reciprocal curve, which is what we call Langmuir-Burke double reciprocal plot. So you take the inverse of V naught, and then you also take the inverse of this right side of the equation. And then you see we have this, you can extend it out, and then you'll see we have the inverse of Vmax of velocity equals Km over Vmax multiplied by the inverse of substrate concentration. And this term become, if you cancel out that substrate part, and then that equals the inverse of Vmax. So now we have this equation, which is the inverse of velocity equals Km over Vmax multiplied by the inverse of substrate concentration plus the inverse of Vmax. So if you do a set of experiment, and then you plot the data, you plot the inverse of velocity as a function of the inverse of substrate, and then you can have a linear relationship. I'll show you the linear shape here. This is what you will get. So that is a plot of the, this is another way, simply another way to write that equation. You see the inverse of velocity equals Km over Vmax multiply the inverse of substrate concentration plus Vmax, the inverse of Vmax. And so that's a very important property of this linear relationship, linear curve. And you see this curve have a slope of Km over Vmax. So that is a slope. So the slope of the curve equals Km over Vmax. And this curve intersects with the y-axis at the inverse of Vmax. So and on the y-axis, you see, at this intersection, the inverse of concentration equals 0. And then you see the velocity actually equals the Vmax inversed. And so extrapolate this curve until it intersects with the x-axis. So that means if you look at this curve, with the velocity inverse of the velocity equals 0, and then you end up with intersection. The inverse of the substrate equals the inverse of Km, negative inverse of Km. So you can see with this kind of plot, if you do a plot of inverse of velocity as a function of the inverse of substrate, and then you can determine what is Vmax, and you can determine what is Km. So because the slope of this plot equals Km over Vmax, and this plot, this curve intersect and on the y-axis at the inverse of Vmax. And it intersects with the x-axis as a negative inverse of Km. So we can do a set of experiment, collect some data and do this kind of plot. And then we can figure out what's the Vmax and what is the Km of the enzyme catalytic reaction. Is there any questions about the double reciprocal plot? Any questions? So now I'll give you an example and see how we apply this double reciprocal plot to figure out the Vmax and Km of enzyme catalytic reaction. And these are some of the data we observed, for example, through an experiment. And so that is the substrate concentration in millimolar. You see 1, 2, 5, 10, 20. And that is the velocity of the reaction and in the unit of macromolar per second. So you see that is 2.5, 4, 6, 7.6, 9. So if you want to do a double reciprocal plot, and then first you do is you take the inverse of all the substrate concentration. You see the inverse of 1 equals 1, inverse of 2 equals half, 0.5, the inverse of 5 equals 0.2. So we calculate all those numbers, the inverse of substrate concentration and the inverse of velocity of the reaction. And then when we do a plot, we have this linear relationship. And then if you look at the y-intersection of this plot, it equals 0.1 macromolar per second. And so then if you take the inverse of this, and then you have the velocity, maximum velocity equals 10 macromolar per second. So that is the Vmax. And you see it's pretty close to this highest number of the, so if you just do that hyperbolic, draw this data substrate as function, velocity as a function of substrate, and you'll see the Vmax is pretty close to 9. But you never have a good idea exactly what it is. And if you you do this kind of double reciprocal plot, and you can determine what the exact number of Vmax. Of course, you can also derive Vmax if you extrapolate this plot until it intersects with x-axis. And so this is what we observe. It is equals the axis, this plot intersect at the x-axis at 0.33, the inverse of millimolar. And then we can derive the Km, which equals 3 millimolar. So like by doing this kind of double circle plot, we can figure out what is the exact Vmax and Km of the reaction. Any questions about this double circle plot? Is there any questions? I want to slow down a little so that you can digest this. Okay, if there are no questions, I'll move on. So we derived the lecture17 equation, and it can be used to describe the velocity of enzyme catalytic reaction as a function of substrate concentration. And so even we know the lecture17 equation, even if we know the Vmax, and we still we do not know exactly how good that enzyme works. And for example, we want to know, like for each 1 second, how many reaction occurs. That will be a very interesting number. And actually we call that turnover number. So the turnover number is a measure of catalytic activity of enzyme, which is saturated with substrate. And so the observed rate constant for that, under that condition is what we call turnover number. And you see, this is definition of turnover number. Kcat equals Vmax divided by ET. So the maximum velocity divided by the concentration of enzyme used. And so this is very interesting number because it describes the number of substrate molecules converted to product for every single enzyme active site per unit of time. For example, every second, how many reaction occurs to the active site of that enzyme. So Kcat equals Vmax divided by ET. So if we go back and I want to show you the equation, and then immediately you see because we determined we defined the Vmax as K2ET when we derived the lecture17 equation. So Vmax equals K2ET, and if you divide that by ET, and then immediately you see, oh, Kcat equals K2. So Kcat, indeed, it is described the rate constant for the second step of the reaction. So here I give you some examples, and you see now, like if you compare the Kcat and you compare every enzyme at using the same kind of standard. And so, for example, catalase, this enzyme, it transforms superoxide into water and oxygen, and it can catalyze 40 million reactions each second. 40 million reactions each second. That's very fast. And carbonic anhydrase is the enzyme we talk about, which transform carbon dioxide into bicarbonate, and it can catalyze 400,000 reactions each second. These are pretty fast enzymes. But of course, there are other enzymes. For example, this RAC-A protein, which is the ATPase, and it only hydrolyzes one ATP like in 0.4 ATP every second. So every 2 seconds, it's only catalyzed the transform of one reaction. So this is the Kcat, which is the catalytic activity of enzymes, the turnover number of enzymes. And so this is very nice number because immediately you know how fast the enzyme works, how good a job the enzyme works, because it describes how many reactions it catalyzes each second. Any questions about KCAT? Okay, so I move on. So we know it's KCAT describe how fast the enzyme catalytic formation product. It equals K2, and so further we want to know like how good this enzyme works, and we want to know like what's the efficiency of the enzyme catalytic reaction, and so how many reaction occurs when a certain number of substrates bind to that enzyme. And so here we introduce this term called catalytic efficiency, which is KCAT over Km. So KCAT divided by Km. And so this upper limit for KCAT over Km is diffusion limit. So that means every time a substrate bump into an enzyme, and then it forms a product. So that means it is a perfect enzyme. And so that is like the diffusion constant is like roughly 10 to the power of 10 mole per second. So that means the substrate bump into the enzyme 10 times 9 times each second. But of course, it's not like every time it bumps into the enzyme, it forms a product. And sometimes it forms product, sometimes it does not. And so here is a list of some of the KCAT or Km of the enzyme catalytic reaction. And you see they are pretty close. Many of them are pretty close to diffusion control. So we know that we can measure the velocity of enzymes as a function of substrate concentration. And actually the enzyme catalytic reaction is very complicated. And the velocity of the reaction can also be influenced by pH or the temperature of the reaction. For example, for this reaction, and you see the rate of the reaction increase gradually as a function of time, and then gradually it drops. And so it's pretty easy to understand because when we talk about protein denaturation, and you see at high temperature, the protein actually got denatured, and then it cannot do its job anymore. And also, here I show you some of the pH profile of a few enzymes. For example, pepsin is very active at low pH and acidic, very acidic condition. And then the enzyme will not become so active at neutral pH. But in our digestive tract, like in the intestines, we have trypsin, and you see trypsin is actually quite active at neutral pH, but it is completely inactive when at the acidic pH. And so the reason for this pH dependence, we'll talk about this later on when we talk about how enzyme catalytic reactions. We still have a few minutes, and we can have a little discussion if you have questions. Is there any questions about the topics we covered today? Okay, so I hope everyone takes some time, read the textbook. The textbook did a really good job and to derive the Michaelis-Menten equation. And even it is a little bit different, like slightly different and from what we did, like you might in this lecture. But like if you understand what we did today, you should be able to understand what how they did it in the textbook without a problem. And so I encourage everyone, take some time, read the textbook really carefully. And this is actually the most challenging part of the whole course for this semester. And we'll definitely have questions in the homework, in the exam, and ask you to apply this Michaelis-Menten equation to answer questions. Any questions before I stop? Okay, if there's no question, I'll just stop there. And I want to remind everyone, spend some time with the text. These 2 lectures is pretty complicated for a lot of people. And if you not understand, you not apply very well. Okay, that's all for today.